Okay. All right. Um, already we lost 7 minutes talking about midterm. All right. So today is about PAC learning. I chose this topic not only because of the promises of riches and machine learning. Actually, today, unfortunately, we'll do theoretical learning theory, so it probably won't make you particularly wealthy. But also, it's going to build on a lot of ideas from last lecture. Okay. So, all right. Let me skip ahead to what we did last time. Right. So last time we talked about sampling, um, uh, and at some level, the kind of sampling and guarantees you get from additive turnoff, except it was in the context of these kind of relatively simple geometric spaces. Like I had points and disks, and I wanted to subsample a subset of points, so that roughly kind of the fraction of points in each disk is still the same, up to some epsilon factor. And by taking advantage of the simple geometry, uh, captured by VC dimension and growth, you can actually get these really, really small sample sizes, much smaller than you would get from the turnoff bound. Since we're going to reuse those tools, let me just remind us then. Here was the additive turnoff bound. Uh, as usual, we have a bunch of independent bounded random variables. And I'm looking at what are the odds that the average of the observed average is deviates from the true average by an additive epsilon or something. Okay, and we got something that was exponentially small in n. Okay, but same general themes. You know, if you have a large number of random variables, it's going to be more and more concentrated. Okay. Um, and we talked about these notions of epsilon samples and epsilon nets. So I want to sample in an epsilon sample, I want to subsample a set of points q, so that the measure, which was the fraction of points in a range R, the percentage of points in a range R, uh, is within an epsilon of the original. Okay. The other object we introduced was an epsilon net. We didn't do the analysis too much, so maybe it's good to remind us here. A point set q was an epsilon net if for every range that contained at least an epsilon fraction of the points, so every kind of heavy range, the measure of R is at least epsilon, Q samples at least 1 point from R. Okay, so you're just trying to hit all the heavy ranges. All right, we didn't talk about this too much, nor did we discuss many applications, but we'll see some applications today. Okay. This will come back later, but a lot of our points of emphasis was this growth function where if I have a fixed set of points q and I'm looking at my collection of ranges R, right? Each disk and I have a bunch of points q, makes a certain intersection with q, right? And a bunch of disks makes a bunch of particular intersections. And the question is just how many different interesting intersections I can make, okay, as a function of the number of points in q. It turns out that for geometries like disks and points, if you have n points and as many disks as you want, you can actually only create like n cubed interesting subsets of your points by overlaying disks. Okay, and the fact that we have this polynomial growth is why we can get these very strong bounds, such as if I wanted an epsilon sample, so I want to maintain the measure up to an epsilon additive factor, you only need really d over epsilon squared if it was a n to the d kind of growth. That's particularly the case for VC dimension d. For epsilon net, we get something similar, except that epsilon squared becomes epsilon. Okay, so we get these better sampling bounds. Okay, so that will come up at the end of today's lecture. So today's lecture is well, one thing I really like about teaching randomized algorithms is randomization touches like everything in theoretical computer science. And furthermore, you can use it to connect a lot of different things in theoretical computer science. So today we'll talk about learning theory, which is quite different than anything we've done to this point. And we're really going to talk about models in learning theory. We're not really going to talk about learning theory algorithms. We're going to kind of talk about models and, to what extent do these algorithms reflect something that we would call learning? Okay, and we'll start with something simple called the consistency model, which is sort of like a straightforward and sort of a deterministic definition. And it's going to have some flaws. And it's going to be corrected by a model called PAC learning, probably approximately correct, that really critically injects randomization into its definition and gives a definition that's more sensible. We'll discuss it. And then we'll talk about topics like generalization error, this notion of Occam's razor, as well as a generalization bound that's stronger using some of the ideas we just discussed involving growth. Okay, but in general, we're going to see some sort of correspondence between quote unquote learning or generalization and all these concentration bounds that we see. It's almost one to one. Okay. All right. So, I don't know. This might not be as hard a lecture as usual, but I guess we'll see. I saved this slide for an example, and I forgot to think of an example. All right. You guys are young and bright. What's an example of a learning theory problem, a classification problem, just any application? Come on. Yeah. Okay. Interesting. Okay, so online code judging. Sorry. Not sure what that means. Okay. So I guess here you're trying to assign a numerical score, like a rating. Okay, so I guess classifying code. Okay, that's relatively. Um, any other algorithm? Okay, yeah, okay. Picture recognition. So image recognition. Here's a picture of a cat. One of the most important problems of this century, at least as measured by funding. Um, other ones I saw include your email. You want to know which ones are spam or not, stuff like that. Um, Whatever. Okay, so there's a gazillion different kind of classification problems. It's hard to even open up the New York Times without reading about another one. But today is really about how to model these algorithms and coming up with some framework where we can try to distinguish one algorithm from another. So I'll start with the consistency model. So, okay, there's a lot of information, so let me go slowly. Okay. So, all right, so there's maybe 4 ingredients in the consistency model. One is the domain, the space of kind of input examples, which I'll denote by X. So that could be emails in the case of classifying emails. Okay. And then you have labels, and for simplicity, we're just going to worry about 2 labels, spam or not, okay, or 1 or 0, true or false. Okay. Now, okay, so all of X is labeled by something, and that's called, in the literature, a concept. Okay, so a concept is some function C that's taking every point in X and labeling it spam or not. Okay. And then we assume that the concept comes from some concept class. Okay, so there's some kind of family of possible functions over X. Okay, it could be any function of X, but typically it's more interesting to look at a somewhat more restricted class, and that also makes the problem more plausible, because at some level you're never going to guess a completely arbitrary function of X. Okay. So the model assumes that your input X is labeled by an unknown concept C, but it's from this known concept class, script C, capital C. Okay. And the high level goal is you get some set of labeled data and you want to identify what is the concept that's giving these labels. Okay, that's sort of high level goal. Not a rigorous model yet, but those are the main ingredients. Okay. So okay. Here then comes more formal definition. So okay, so what does it mean to have a learning algorithm in a consistency model? This is just a definition, not like an opinion. Okay, so your input is going to be some training set of data. So X represents like the email, and Y1 is like spam or not, the label. Okay, so each yi is going to be cxi for this unknown c. All right, so a concept c prime is consistent if it agrees with all of your training data. And a learning algorithm in the quote unquote consistency model is defined as an algorithm that, given this training data, can either find you some consistent concept or declare that no such concept exists. Okay, so you basically have a big family of possible labels, and you're given some labeled data, and you just want to find one of them that agrees. Okay. Now, in general, your concept class is not like a set of 10 possible choices. It's some like our pretty large thing. So what you can't do, at least in any interesting case, is just try them all out and check that they agree with all the training data. So these are going to be algorithms that are doing something clever. Of course, I haven't given you examples of concept classes yet, so it seems a little abstract at the moment. Hopefully one is coming up. Disjunctions. Okay. So let's say that your input's like bit strings of a fixed length. So I guess in that example, you have 5 bits, for example. Okay. So here I have the XIs, and here I have their label, and they're even color coded for you, which is nice. Okay. So uh, a disjunction is just an or of variables, right? So it could be x1 or not x2 or x3 or whatever, right? So the concept class may be disjunctions. So that means that this data and this labels must correspond to some disjunction. And I guess I chose not x2 or not x5, where x2 refers to the second column, x5 refers to the fifth. I hope that's true. Is that actually correct? I once convinced myself it was correct. Yeah? Okay. All right, so this is a plausible concept for this set of data. Now, the problem that would be presented to you is, if you wanted to come up with a consistent learning algorithm, is I would give you this data set, and you would have to come up with a consistent disjunction. Okay? So, of course, you already know one that works, but in general, you're given some data set, and you're going to want to define some disjunction C based on your data. All right? So, I should mention that all of these algorithms should be reasonably efficient. So brute forcing all possible disjunctions and seeing which ones work doesn't count as a great algorithm. Okay, so we want to do something more clever than that. All right, so you guys might be able to guess this. What's it a reasonable way? Yeah. Okay, we'll go one column at a time, one feature at a time. Okay. Okay, so I think we'll do this one together, see if it works. But the idea is to go one feature at a time, and if like all the positive labels and all the negative labels have like the opposite 1 or 0, then add the corresponding thing to the formula. Okay, so let's see if that works. All right, so let's look at the first column. Is there any agreement? Okay. Second column. Okay. Third column. Okay. Fourth. Okay. Fifth. Okay, so this algorithm produces the empty formula, which is also declaring all labels to be false. Okay, but that's actually quite a sensible algorithm. When I first heard it out loud, it wasn't obvious to me that we were not going to generate anything interesting. Okay, but there was clear what the logic was, right? So the idea was, oh, can we find some really obvious columns where obviously I should put in either x1 or not x1? But it turns out there was no obvious ones in this particular set of data. Okay, so this is not an obvious problem, but you guys might still be able to guess an algorithm. So that approach was too strict in a way. We weren't generating enough. Yeah. Okay, that's not a bad idea. So let me write that down for us then. So let me write z1 or not z1 or z2 or I hope I have enough room or z3 or not z3 or z4 or not z4. Damn it. Science. Or z5 or not z5. Okay. And now we're going to go through and eliminate any of these symbols that are leading us astray. Not even 100% sure what that means, but I'll let you guys decide what it means. All right, Z1, should I get rid of Z1? Okay, I guess because it would mislabel this row. Oh no, it would mislabel these rows. Okay, what about not Z1? Yes, I should eliminate. Okay. All right, what about Z2? Eliminate. Not Z2? Keep. We got to keep her. All right, Z3? Should I keep it or kill it? Kill it. Okay. Killing sounds pleasant. Not Z3? Get rid of it. That's nicer. Z4? Keep it. Not Z4? You probably want to eliminate anything that's the opposite of something you kept. Z5? Kill it. Not Z5? Keep it. Okay. How do we do? Does this work? Sure, sure. But let's focus just on consistency. This is consistent with the data. Okay, cool. How fun. All right, so see if I did one of these things. Guess not. Okay, so here then is would have been is the algorithm kind of put in more constructive fashion. It should be the same as the elimination idea we just did. So, okay, so I'm going to have a bunch of either zi's or not zi. I'm going to include zj if for every sample that's negatively labeled. So whenever yi equals 0, I had xi1 equal to 0. That means it's safe to include it. And I'll include not zj if the corresponding, this notation makes no sense. Okay, so those should be zij's, and I mean xij's. Xij being the jth coordinate of sample xi. I'll include not zj if xij is equal to 1 for all of the negatively labeled examples. All right. Okay, so fine. Um, okay, so I guess one way to try to argue this thing is um, true. Okay, so I want to make sure that all negative labels are labeled negative and all positive labels are labeled positive. Okay, so if something is labeled negative, just on our data set, I want to just show it's consistent. If something was labeled negative, um, well, then I'm only worrying about when yi is equal to 0, and I'm only setting zj, including zj, when xij is always equal to 0. So that won't that won't mislabel any of the negatives. And I'm only including not zj when I know that that feature is always 1 on all the negative labels. So again, in other words, our two choices are kind of designed to be safe with respect to all the negatively labeled. But I guess maybe what's not obvious is why this would correctly label all the positive examples. Okay. So one idea is to try to prove this is try to argue this following claim. So let's say there's some true disjunction C star. Okay. The claim is that C star is kind of always a subset of C in terms of like the symbols it contains. Should always be a subset. Okay. So why is that?
The data set we have is generated from a concept, right?
Well, the X's are sort of the choices of, yes, the Y's correspond to a true concept.
So it's impossible for the data set to like self-conflict and not match any concept.
That's right. We're assuming that the input data was labeled by a concept in the concept class. We don't know which concept, but we know it came from a disjunction. So the claim is that our formula kind of contains whatever is the real formula. Okay.
If the real formula contains just one more thing that our formula does not contain, then it must have contained something we excluded. But we excluded that because it was inconsistent with one of the data. So if the true concept included that one, it would be inconsistent with the data that caused it to rule it out.
All right, let me see if I can rephrase that. So let's say that some symbol zj, it could be bar zb, but let's say zj for simplicity, does appear in the true formula. So I'm just writing zj and C star, I'm just making up notation. Okay. Then we know that C star labeled our training set, right? So whenever yi is equal to 0, we must have xij equal to 0, because otherwise C star would have labeled it 1. Okay, so if some symbol appeared in C star, then we must have xij equals 0 whenever y is equals to 0. So we would have put zj into our formula as well. The same argument for if bar zj was in C star. Okay, so this algorithm is, well, maybe it's more clear from the elimination version, really trying to throw in as many symbols as possible and agrees with the formula. Okay, all right, so that addresses the true. Okay, So now if C star is a subformula of C, the claim is that that will ensure that true instances are labeled true by our constructed formula. Why?
Because it's disjunction. So if it's true in the sum formula, it will be true when we tack on.
Yeah, so sub just adding more symbols is just more excuses to label something true. So if C star labels something true, then C, our C, which is certainly bigger, or is at least as big, will also label it as true. Okay, so then we get true is true. All right, so that's why it's consistent. All right, it's non-trivial, I guess. All right, okay, so much for that. All right, let me give another example. Suppose all the points are coming from the 1 by 1 grid, square, and my concept classes correspond to rectangles. Okay, so maybe outlined in yellow is a true concept, and so the points inside are colored red, which I guess means true, and the points outside are colored blue, which means negative. Okay. All right, what would be a consistent learning algorithm for this setting? Remember, you can't see the yellow square in your data. You just see the red points and the blue points. Yeah. Okay, so should I draw a rectangle like this size out here? Ah, okay. Oh, that doesn't normally happen in machine learning. Okay, so we can try to make, in some sense, like the smallest rectangle that contains the points. Okay, makes sense to me. And of course, it's a simple algorithm, right? Because you just go through the red points and figure out, oh, what's the rightmost point, what's the leftmost point, what's the highest, what's the lowest, and that gives you your 4 boundaries. So it's quite simple. Any other algorithms? You can also try to do the largest rectangle that fits in it. Okay. So the largest rectangle, which also can be done efficiently by kind of figuring out, I mean, it's a little more complicated, but nonetheless, it shouldn't be too tough. Um, Something like that. So, all right, so you can now put the smallest or largest rectangle that contains exactly the positively labeled points, and that'll be a consistent learning algorithm. Okay. All right. So, all right. Are people satisfied with these algorithms? Yeah.
I think in rectangle size parallel to
Oh, yeah. I guess here we're assuming axis parallel rectangles. That'll also be true when rectangles come up for the rest of. Yeah. Sorry, I should have said axis parallel rectangle. Okay. All right. So, are we really satisfied with these algorithms? We do output a consistent algorithm here, but I don't know. We're not really outputting the yellow rectangle, right? We're just getting something consistent with the training data. If I output something here, depending on which square we choose, we may get it wrong. Or output something here, we may get it wrong, right? If I had drawn this picture to be more exaggerated, like the red points are really a small cluster in the middle and the blue was really spread out on the boundary, you'd see a big difference between the big square and the small square. All we know about yellow, it's somewhere in between, but if there's a big difference, it's not saying much, right? So, is this really a learning algorithm, right? Just trying to find some shape that's consistent with the data, right? We're not asking the algorithm to output a concept C prime that reflects C star anywhere outside of the training data, right? So there's no guarantee that you have some particular arbitrary training data. There's no guarantee that's going to generalize to anything outside. It's just not included in the model. It's not an issue. It's not part of it. So while of course getting something consistent with the training data might seem very natural and it's obviously desirable, you could argue that, you know, what we think of as learning is not really this. Okay. All right. Any questions to this point? All right. So this is when we bring in this notion of PAC learning, introduced by Valiant in 1984. That's Paul's dad. Paul's a professor here. Okay, so we'll start from the same setup as consistent learning. So we still have concepts, domains, labels, stuff like that. And okay, so what are we going to add? That's okay. So for whatever reason, we are going to, before we had concepts that labeled data and we were choosing concepts to try to guess it, we're going to kind of separate that. We still have concepts that are truly labeling the data, but we'll allow for like a different family of hypotheses, okay, which is what we'll output. So it's possible that the set of hypotheses coincides with the set of concepts. H equals C is allowed, but it could generally be a different family. Okay? That's sort of besides the point. More important is that, okay, I'm going to assume there's some fixed distribution D over the example space. That wasn't part of the definition before. Okay? But now I'm assuming there's some distribution D from which points are drawn, like in real life. There's some distribution over emails, real distribution. I don't know the distribution, but I'm assuming it's fixed. Okay, that I could sort of draw training samples from distribution and it'll reflect the real life distribution. All right. Now for a hypothesis H, okay, we can define sort of a true classification error that sort of does nothing to do with training samples. Okay, so this is your hypothesis H that maybe some algorithm produced. And I'm saying, okay, what are the odds if I draw X from D that H disagrees with the real label? So C is the true concept that's actually labeling these things. It's classification error. What are the odds that I disagree? Okay. So the high level goal, naturally, is to try to find a hypothesis that minimizes the true classification error. That makes some sense, right? I want to get as many right as possible on some real fixed distribution of data. Okay, so but how do we kind of, we haven't defined what a PAC learning algorithm is. So here we go. Okay, so what's the definition? And so this is the definition that turns out to be more robust and that we end up working with more. Let's fix epsilon, delta, and delta between 0 and 1. Okay. So a PAC learning algorithm, there's sort of a strict definition. It's going to take an input, a set of labeled data points, but the x's are going to be drawn from the distribution and the y's will be the corresponding labels. Okay, so we assume that the labels are coming from this distribution that we're also trying to target in our classification error. And, okay, so the learning algorithm is going to output a hypothesis. Okay. Now that choice of hypothesis is probably randomized because for one, the input that it's based on is randomized. Okay, so we're not going to require the algorithm to always have a very good hypothesis. We are going to say that most of the time it should. So with probability at least 1 minus delta, it outputs a hypothesis where that classification error is at most epsilon. Okay, so you get to give the input epsilon and delta, but maybe delta is like 1/2, so you just want to be right half the time, and epsilon is some error 10%. So you want a classifier, a hypothesis with 10% error at least half the time. Okay. But this is kind of much more general, right? It's not some arbitrary function of the training data. Yeah. Okay, so it's sort of a natural randomized analog of the consistency model, but one that sort of incorporates aspects of real world generalization that are essentially omitted from the consistency model. Okay, so that's probably approximately correct learning. Questions? Okay, so this is just for our intuition. We'll do some more detailed analysis later. But that example of axis parallel rectangles, suppose your distribution was uniform over that 0, 1 square. Okay. Then you're hoping that as you sample more and more points, you'll get more and more points that are like closer and closer to the boundary of the real concept, right? And as these sampled points do approach the boundary, that strategy of the closest and furthest containing rectangles, or smallest and biggest, sorry, is going to more and more converge to each other. And they're going to surround the true concept, right? So if we assume that the input data is coming from a nice distribution like uniform, then you could start, you can imagine doing a bunch of calculations. You fix the true concept and you start calculating, oh, what are the odds of getting very, very close to that boundary and so forth. And you can actually do some rigorous and exact calculations and eventually show that actually your algorithm is a PAC learning algorithm. You will, with poly epsilon points, kind of approach the true concept. Okay. We're going to do it in a more slick way at the end of class using some of those tricks from last time because we know this is sort of a small VC dimension range space. Okay. Yeah. Yeah. So we're assuming that there is an underlying concept class that's correct. So in other words, the point lands, and then if it's in the yellow, it's automatically red. If it's outside the yellow, it's automatically blue. So we're assuming everything's correctly labeled. You can take all our models and say, oh, what if you have a noisy concept that sometimes flips things, and whatever. You take everything we do and you add one more layer of nuance. Same ideas will hold. It's mostly for simplicity and focus on the. All right, so let's talk about how to get generalization bounds. Okay, so here's then it will be the first theorem we do. Got to make sure we make good time. All right, so M refers to the number of pieces of data in our sample set. Okay, so we have M points drawn from this distribution D. And here we're going to look at the case where there's only a finite number of hypotheses. Okay, this is sort of the simplest bound we'll do. The claim is that if M is at least log of the number of hypotheses divided by delta divided by epsilon, then was probably at least 1 minus delta, all the consistent hypotheses, so any hypothesis that's consistent with those M points, will have true error at most epsilon. Okay, so if you have a fixed and finite number of hypotheses, then if you have roughly log of this number of hypotheses divided by epsilon, then any hypothesis consistent with your data will have true error at most epsilon. Okay, so why is that useful? What happens, so let's say that you had a consistent learning algorithm for this particular concept, class, and hypothesis. Okay, so suppose you had an algorithm that, given any set of data, can give you a hypothesis that's consistent with it. How does that relate to PAC learning? Yeah. Yeah, okay, so a PAC learning algorithm needs to find a hypothesis with small error, small real error, and you have an algorithm that knows how to get sort of zero error on the training data. But this theorem says that if you have enough training data, then zero error in the training data will translate to epsilon error on the real data set with a certain good probability. Okay, so if you're sort of treating the number of hypotheses as sort of a fixed and constant parameter, because the number of samples is supposed to be polynomial in epsilon and delta. So if you're not too worried about log of h, you just focus on the epsilon and delta, then it's really saying kind of log of 1 over delta divided by epsilon points is enough to get you a classifier with epsilon error. Okay, so this will relate kind of consistent learning with PAC learning for the special case of finite sets of hypotheses. It's exciting. All right, how do we prove this? Okay, well, let's say that a hypothesis H is bad if error of H is at least epsilon. So these are the hypotheses that I don't want a consistent learning algorithm to output, right? So in particular, I want to show so the goal now is to show all bad H are inconsistent with that probability at least 1 minus delta. Okay, so what if I wanted to bound? So let's say that H is bad. I want to bound the odds that H is consistent. Right? Okay, how might I do this? Okay, so a particular point, we randomly sample one point, and there's an epsilon chance that it'll be one of the points, or at least an epsilon chance that it'll be one of the points that sort of kill off this hypothesis, right? Because it'll be one of the points that the hypothesis gets wrong, and the consistent learner will therefore ignore it. Okay, so that's one of them, but if there's m points, what should I do to this? They're independent, yes. Huh? So you raise it to the m. Okay, great. And then? Okay, we can substitute. What am I doing? So many parentheses, I'm getting confused. Okay. Number of hypotheses divided by delta divided by epsilon. Okay, hope that's not too confusing. Okay. We only do one thing in this class. Besides the need of expectation, we do like, okay, arguably 2 or 3 things. Yeah, it's not roughly. 1 plus x is always less than or equal to e to the x for any x. So we can put this x thing in the exponent, e to the negative epsilon times this term we just had. It should be an absolute value. Something like that. Delta over the number of hypotheses, right? Okay, so that's for 1. How do I make sure that none of the bad hypotheses turn out to be consistent? A union bound. And how many bad hypotheses are there? At most, the number of hypotheses, right? So now union bound over everything completes the proof. Okay, simple enough. Okay, all right. So let's apply that now to our beloved disjunctions. Okay, so we had this consistent learning algorithm on our second attempt. All right, so for a fixed number of features, so n is fixed, the number of bits in the data, how many possible disjunctions are there? 2 to the 2 to the n? 2 to the 2n? Okay, that's also known as 4 to the n? Okay, can anyone do better than 4 to the n? Yeah, 2 to the n? You can't quite do 2 to the n. 3 to the n. So each variable is either x1's in there or not x1's in there or neither of them. There's no point in having x1 and not x1 in there. So, okay. Of course, we're not really fighting for anything important, but 3 to the n. Okay. So this theorem tells you that if m is at least roughly log n over delta divided by epsilon, then our consistent learning algorithm is a PAC learning algorithm. Okay, so just listing all these variables. Okay, will meet the criteria for PAC learning insofar as we're treating n as a fixed parameter. Okay, so disjunctions are PAC learnable, at least for fixed n. Question? Look up set. 3 to the n? Oh, wait, what did I write? Oh, yeah. Let me do it correctly. N plus log 1 over delta. Good, good. Just keeping you on your toes. All right. Okay, let me talk about a slightly different kind of bound. So for a fixed set S, we can define sort of the error with a fixed training set S. I could define the training error to be the fraction of that training set that you get right. Okay, so error sub S of H is exactly, how many things did you get wrong divided by the total number of samples. Okay, so it's your score on the training set. Okay, so if you have a consistent learner in a consistent setting, the previous one is great. But in other settings, other algorithms may simply just try to find a hypothesis that minimizes the training error. That's very natural, right? If you minimize the training error, you want to know that it'll generalize well to the real error, right? That's what this is. What's the difference between the real error and the training error for a particular hypothesis? Okay. And I should mention, you really want all of the hypotheses to have this small, right? So for example, whatever is the best hypothesis out there in terms of true error, you want the sample error to be small too, so your algorithm has a good chance of picking it, right? On the other hand, the bad hypotheses was bad actual error. You want the training error to also be bad so that you don't output it, right? So you want the bad things to still look bad. You want the good things to still look good. So you really want all the hypotheses to be close to each other. Have a small gap between the true error and the sample error. Okay. All right. So what is sort of the implication of this? If you have an algorithm that can basically minimize error S of H, or at least get it down to epsilon or something, then that'll give you a PAC learning algorithm. Okay, so if there is a hypothesis with true error, like at most epsilon or epsilon over 2 or something, then if you make M big enough, then an algorithm that gets you the hypothesis with the best training error will also approximately get you very good true error. Particularly, you'll get under epsilon for your desired epsilon. Okay, you might replace some epsilons with epsilon over 2's so that 2 epsilon over 2's make an epsilon, but that's not a big deal. Okay. All right, so that's why this is useful. How might we prove this? Okay, it kind of almost looks like additive Chernoff, kind of almost looks like. Anyone want to go further than kind of almost looks like? It kind of almost looks like would only get you partial credit on the midterm. Yeah. It'll get you kind of almost full credit. So how would I apply additive Chernoff?
So you can break the absolute value into one greater than and one less than.
Yeah, okay, so that's two inequalities in there, so we can just worry about one at a time.
And then ER of H is essentially the mu in the added turnout map. So we can pull that to the other side.
Okay, so let me make it a little more clear. So you need some kind of x1s through uh, xk or something, right? But what would xi be? What would k be as well? Okay, so one if, so here we're going to fix h, and we'll take a union bound at the end. So I'll say one, and so what you have to assign one of these to be 1 and one of these to be 0. Which one do we put? Right? Okay, then what does the sum of h xi's give you? So it's actually counting the number we get right because you did 1 if it gets it right and 0 if it gets it wrong. So we're going to flip that. Okay. All right, so now x1 plus xm over m is the empirical error. Okay. So how many get wrong out of the total? And the expected value of error sh, as already mentioned, is the true error. Right? That's how much you should get right. So this is exactly the kind of thing that goes inside the additive Chernoff bound. I don't know if you guys can see, but there's a very small additive Chernoff bound there. So whatever, the probability that one error minus the other error is at least epsilon is going to be at most, I'll just do both inequalities at once and put a 2 in front, 2 to the e to the minus, whatever, 2 epsilon squared m or something like that. And m had a log of the number of hypotheses and also a delta, and then something to cancel out the epsilons. So you should get delta over the number of hypotheses. Now you can take a union bound and, okay, all of your hypotheses will have small gap in those true error figures. Okay, so these are just actually expressions of calculations we've done many times before. But what are some interesting implications or ways to look at it? Okay, yeah.
So we're assuming again that S is
Oh, or S is coming from, so in the context of PAC learning, I'm assuming that the samples, both in terms of the true error and the training data, is coming from the same fixed distribution D. Yeah, and that simple example is uniform because it's easier to think about, but whatever the real world distribution is. Yeah.
these samples previously training data expected.
The sample space more, or X, yeah, or the training data comes from the sample. X refers to just kind of the space of things that get labeled, like emails. And D is a distribution of emails, the real world distribution of emails. S is a set of M emails drawn from this real world distribution. Okay. So anyway, that's how we get these finite hypotheses. It turns out to just be taking union bounds. It's not even technically that interesting. I mean, from a pure calculation point of view. All right. Let me talk a little bit about one of these learning theory concepts. Okay, so you guys might have heard of Occam's razor. That is the notion that we should prefer simpler explanations. There's lots of famous people throughout history who have expressed this. From my perspective, William Occam is probably the only person I hadn't heard of, except for this expression. The others have more independent. I think he actually was significant. So Aristotle, Isaac Newton, Bertrand Russell, Einstein. It's always a big thing in physics, right? The idea that you have these small, it's kind of simple laws of physics. Richard Feynman. I found. Anyone know who the big Aristotle is? Well, you guys know who Aristotle is. You have some Greeks, I think. Who's the big Aristotle? Oh yeah, the Shaquille O'Neal. Okay, so I think he had some quote where he just wanted the ball. So he said, if you don't stick to simplicity and give me the ball, then you'll lose. Okay. All right. Okay, but the general idea is we should prefer simpler explanations, or what we'll see here is simpler hypothesis classes, and we'll get better bounds. But let me explain. Okay, so how do I measure simplicity in computer science? By the number of bits it takes to write it down. Okay, so let's say that I'm looking at a class of hypotheses where every hypothesis can be written in b bits for some parameter b. Okay. All right, so the first claim is that if m is at least b plus log of 1 over delta divided by epsilon, then with probability at least 1 minus delta, all the consistent hypotheses will have true error at most epsilon. Okay, sort of analogous to the first result we just proved. The next one is analogous to the second. If m, the number of samples, is at least b plus log 1 over delta divided by epsilon squared, then with probability at least 1 minus delta, the gap in the two errors is at most epsilon for all hypotheses. Okay, all right. How do we prove this? You guys can do this. Yeah, so at some level, I don't know if you can see, but these were the things we just proved. Maybe you can't see. But we used to have a log of size of hypothesis term in there. It seems to have been replaced with b. So how do we do that? So if everything can be expressed in 10 bits, there can only be 1,024 hypotheses, which is 2 to the 10, right? So 2 to the b is an upper bound on the log of the size of hypothesis. And so this is really just expressing what we just did. But it gives you some generalization bound in terms of number of bits of the underlying hypotheses. Okay. All right. Okay. I don't know why I have the same slide again. All right. So we have 10 minutes. I promise you we'll make some connections to last lecture. So here it comes. I should mention that actually I forgot to make a slide about one more bound related to bits in Occam's razor. But just check the notes. It's hard to explain. Okay. It's not hard to read. It's just saying, well, is it worth it? Yeah, let me write it down. It'll say the following. For all h and h, it's more or less the same argument as we just did, but it's going to take a certain union bound over things in a clever way. The probability of Okay, so we're looking at a hypothesis class that can have any number of bits in each hypothesis. Okay, because we're going to get a different kind of error bound for each hypothesis as a function of the number of bits. Let me explain. For all h and h, the error, the true error minus the sample error, let's see if I can get this right, is at most the square root of b plus log 1 over delta over m, something like this. Okay. So in other words, here m is fixed, although it probably needs to be bigger than b plus log. Let me replace b. This is the b just for this hypothesis. Okay, so the number of bits that's in describe the hypothesis. Yeah. What is this? Oh, I shouldn't have mentioned this. This has just gotten me in trouble. Okay. Uh, Probably that this thing is bigger than epsilon, which means there should be some dependence on epsilon here, maybe. I don't know. Okay, I should have just never mentioned this, but at some level, I may have screwed up the right-hand side, but at some level, you can guarantee that the difference in error is something that depends on a number of bits in h. Okay, and that sort of comes from flipping upside down how big m needs to be to get a certain delta and epsilon from the previous bound, and bucketing. You take your full class of hypothesis, and you break it up into what are the hypotheses between 1 and 2 bits, 3 and 4 bits, 5 and 8 bits, 9 and 16 bits, 17 and 32. So you bucket in powers of 2, and then you could do some tricks where you make delta go down by a power of 2, and you could take a union bound thing. It's at some level inverting what we just did before and applying it to powers of 2. Okay. Yeah, so shorter hypotheses generalize better, as Shaquille O'Neal once said. Okay. All right. Now I have less time for this. Generalization bounds by growth. Okay. So every hypothesis I can think of as a range. I mean, that was clear in the example was rectangles where it was quite literally a range, right? And the question is, okay, if H has a relatively simple geometry, can I get better generalization bounds? All right, so just to remind us, okay, the growth rate is kind of how many interesting subsets you can carve out with the ranges, right? And then they had epsilon samples, epsilon theorems, and we're going to figure out how to use those. All right, so here then are the bounds. So these are the strongest ones we've had yet. In particular, they apply to hypotheses classes that are infinite, right? Before everything was finite, we don't have that restriction anymore. Okay, so if m is at least the growth rate of 2m over delta divided by epsilon, then we have this kind of consistent learner implies, I forgot to write something important, PAC learning. So all consistent hypotheses will have error rate at most epsilon, just like the first class of results we've had all along. And the second one is, I got that wrong too. Okay. If m is at least the log of the growth divided by epsilon squared, then you'll get this sort of generalization error of epsilon with probability at least 1 minus delta. Okay, so you can see that this clearly corresponds to the bounds that we got from epsilon nets and epsilon samples, respectively. Okay, so there's some connection there, although it's not as direct as you would think. Okay, so let's try to figure this out. Okay, so let's take just the purple one. At some level, I want to figure out how to apply the epsilon net theorem to this setting. So epsilon net theorem says that if I sample roughly that many points, then every range with measure at least epsilon is going to get hit by at least 1 point. Okay? So in terms of hypothesis, let's define a measure. At a high level, I would like, if I want to think of H as a hypothesis, I want to define, I would love to define the measure of H as equal to the error of H. Okay, I'm not saying we're going to do this exactly. Okay, but if I can make some kind of correspondence between the measure of H with the error of H, then that's sort of what I want, right? Because it's saying, okay, anything with error H that's big, anything was, so what did we argue before? We said, oh, let's call hypothesis bad if its error is at least epsilon. Okay, so for a bad hypothesis, if I had something like this, so that the measure of a bad hypothesis is at least epsilon, then I want to sample points so that I kind of hit it with one of the mistakes. Okay. All right. So setting this up requires going a little bit out of our way and not sort of working with directly with the ranges you would think. So let me try to set this up in what time we have. So just not much. All right. So we need a range space PR to make this thing work. Okay. So I'll just run through it. So I'm going to define P to be this space, which sort of corresponds to the data plus the label. Okay, the 0, 1 corresponds to the label, and X is whatever the emails. All right. Now, for all hypotheses, okay, we have the range RH, which is going to be the set of points X, and then 1 minus the label over all points X. Okay, so this is a little bit funky. So it might have been more natural to identify a particular hypothesis with X and its label, but we're going to do the opposite. Okay, so we're going to do X and the opposite of its label. 1 minus HX is just going to turn a 1 to a 0 and a 0 to a 1. All right. Okay. And we're going to now define a measure based on the distribution. So I'll write U sub D. And this will be the probability that if I draw X and Y from D, or I draw X from D and Y, I guess the according label, what's the probability that this point is in the corresponding range? Okay. And then one thing nice is because R sub H actually represents the opposite. Okay. This happens to be equal to the probability that as XY is sampled from D, H of X is not equal to Y. That's why we set up R sub H to be this 1 minus thing, is to get that not equal at that stage. So it is indeed equal to the true error of H. Okay, so I'm kind of translating between one language and the other from this lecture and the last lecture. And we have to do this 1 minus so that the measure corresponds to the error. Okay, so what we need to do, so let f of n be the growth rate of, so I'm going to call this whole set, I'll call this will be my ranges. Okay. The claim, I know I'm overboard, is that f of n is at most g squared of n. Okay. If that was true, then everything would basically follow. Okay, so because we're going to take the log of the growth rate to get an epsilon net, and log of g squared n will be 2 times log of gn. So the 2 just hides in a constant. Okay, so if I can show that this range space has this growth rate, which is at most g squared n, then I can just apply the epsilon net theorem and the epsilon sample theorem to get those generalization bounds. So all that's left is to do this. Let me keep going. Okay. All right. Okay, so here's what we'll do. We want to prove that this growth rate is at most g squared n. Okay, so let's fix set S of m labeled points. Okay, so S is, hoping we're almost done. I'll figure out how to skip some steps to make it a little shorter. Okay. Okay. So we need to show that the number of kind of interesting intersections we induce is at most g squared m. Okay. So what I'm going to do is I'm going to let S0 prime be the set of xi's where xi0 appears in S, and I'll let S0 be the corresponding tuple times 0. Okay. And I'll do the same thing for S1 prime and S1. Okay. And now maybe there's maybe two parts of this proof, and here's one step. The first is that the number of interesting intersections I make with S is at most the number of interesting intersections I make with S0 times the number of distinct intersections I make with S1. Okay? So at some level, because what's happened is I've taken X and I've sort of duplicated into a 0 layer and a 1 layer. And that's the only reason why the geometry's changed a little bit from the original geometry. And here we're sort of getting it back. So I want to figure out the number of combinations in sort of this 2-layer system that has zeros and ones. Okay? But here I'm saying, oh, you can analyze just the 0 layer by itself and the 1 layer by itself. Okay, so why is that true? Well, if you have two different intersections on the 2-layer system and they're different, then they're either different on the 0 layer or they're different on the top layer. So you can charge the one to the other. Okay, and you get the product. Okay, so I think all we have to do is bound RH and S0, the number of intersections looking at just the 0 layer, and then the S1 will obviously be similar, and you guys probably couldn't care less. Okay. All right, so let me finish. I'm almost done. In my defense, we talked about the midterm forever. Okay, so for H and H, okay, if I look at the intersection of sort of RH and S0, this is exactly the set of X0 in S where H of X is equal to 1, just because RH flipped a bit. Okay. I can think of that as the intersection of sort of what was classified as 1 by this particular hypothesis and all the points sitting at layer 0. Okay. Okay, so once I'm looking at one layer, at some level, we're kind of zooming into the layer. So this implies that the number of intersections I'm making with just the 0 layer is sort of the same number of intersections I would make if I was looking at the ranges induced directly by the hypotheses with the 0 layer. Okay, so H here is referring to all of these ranges, all the positive classes. Okay, and this by definition, by assumption, had some growth rate g of m. Okay, so at some level, all we've really done is just look at the 0 layer by itself, and then I can apply my growth rate I had for the hypothesis class originally. Okay, so I guess that's basically the proof. We want to know the number of intersections with sort of this points times labels. And we've sort of broken it down into a product of intersections with 0 labels times intersections with 1 labels. And then one of those layers at a time just follows from the original growth of one of these hypothesis classes. So that's the high level idea. You can imagine S1 is analyzed very similarly. Okay, then that's it. And that wraps up PAC learning. Thanks, guys.